Okay, good afternoon or good night, depending on where you are, everybody. And thanks for being here again in our seminar. Today we have two speakers, Gabriel Pateirnain and Christian Morales. Gabriel is an Uruguayan born mathematician, well known in PD, and Christian as well. So Christian is Spanish, I guess. And today, Ana will be presenting Gabriel, and Diego will be presenting Christian. So Ana,
okay. Thank you very much, Felipe. Thank you very much, Professor, for accepting the talk in our seminar. I will just say some words presenting you. So Professor Gabriel Pateirnain is a professor of mathematics at the University of Washington and fellow of Trinity College in Cambridge. He obtained his licenciatura from Universidad de la República in Uruguay and his PhD from SUNY Stony Brook University in New York. Before coming to Washington, Gabriel spent over 2 decades at the University of Cambridge, where he was head of the department during several years. His research covered an ample mathematical landscape, including Hamilton dynamics, symplectic geometry, and geometric inverse problem. He is author of 2 books, Geodesics Flow and Geometric Inverse Problem, written jointly with Mikko Salo and Gunther Ullmann. So today he will give a talk entitled Geometric Inverse Problems in 2D, a transport twistor perspective. So welcome, you can start. Thank you very much.
Okay, well, thank you very much for the invitation. It's a pleasure to be here today with all of you. I guess what I would like to tell you about is actually connected with the book that Anna just mentioned that came out last year, written jointly with Gunther and Mikko Salo. I guess you had Gunther talking in this seminar, so this might be sort of related to things that Gunther mentioned during his talk. So what I would so let me tell you first what I would like to tell you about. So I'm going to sort of give some sort of general introduction to the problems in geometric inverse problems, and I will try to sort of explain what I mean by that. And the emphasis is mostly going to be in dimension 2. So at first it's going to be kind of pretty general, and then we're going to go to the 2-dimensional case that has its own features. I will try to tell you a little bit how some of these ideas have actually evolved. So it's essentially, it's a story that runs through maybe, one could say, 20, 30 years, basically. And something that has happened in the past 3 or 4 years is that there has been the sort of introduction of a new element in the game, like a new player, which is this sort of complex surface that I will try to explain and what it does. And towards the end, I will just discuss briefly some current developments. So this will give you some sort of overview of what is going on. Okay, so that's the plan for the talk. So let me tell you first what the playground is, where the objects are going to live. So the talk will have a little bit of a geometric bias, but if you're not familiar with some of the geometric aspects that are going to surface, it's going to be very easy to, I'm going to give you 2 or 3 very easy examples in which everything that I'm going to say is already non-trivial. But the general sort of setting is you take an arbitrary compact Riemannian manifold with boundary. And essentially what you do is you look at what is called the unit tangent bundle, which are just points and vectors on your manifold that have length 1. So basically you want to think that you're looking really at a point x on the manifold and a sort of tangent vector v, and this has norm 1. We will see in a reason why this is a good place to work, but this is essentially, you want to think about phase space with energy 1, basically. what is going on. Now, the unit tangent bundle has its own boundary. So if you have a manifold with boundary, you look at now points and vectors, and it has its own boundary. And the way to think about this boundary is that you essentially just place yourself at a sort of boundary point, and then you have a bunch of vectors, and they can point inside or outside, basically. So you divide those sets of points and vectors into two classes, those pointing inside and those pointing outside. I call this the outflux and influx boundary. So with a plus, you have a vector here pointing inside. So you have the point and your vector, unit tangent vector pointing inside. So that's part of your influx. And your outflux, you have a point and tangent vector pointing outside. And nu here is just the inner normal. So these are two sets that are going to be kind of pretty important because there's going to be sort of information going in and coming out. That's essentially the setting of a lot of these inverse boundary value problems. Okay, and one assumption that we're going to make that makes life very simple, but is still fairly general and very good, we are going to assume that the boundary is strictly convex. So once again, if you are actually familiar with the geometric language, that just simply means that you have positive definite second fundamental form. If not, just simply think about this sort of domain in Rn, and it's the usual sort of definition of having something convex. Anything will work here, will be fine. Okay, so this is the basic playground. So we have this sort of basic Riemannian metric in the background, and then we have this sort of manifold that could be in principle very general, and we have vectors pointing inside and outside. Okay, now we want to make some assumptions on the geometry, and one key assumption that we're going to ask is that the geodesics are not being trapped inside. One can discuss all these sort of set of questions when there is trapping, but that's not what I'm going to do today. That will take us in a different sort of direction. The non-trapping case, it is already very interesting. And to sort of say this, that is non-trapping, we're going to call tau the times that the first time where a geodesic, which is just a curve that minimizes length locally, that actually begins at a point xv, takes to exit. So maybe I can draw a sort of quick picture so you know. So this is your manifold M, this is your point X, and this is your vector V, and you sort of look the time that it takes for the geodesic that begins with those initial conditions, X and V, to exit your manifold, to sort of become, you know, a point and a direction in the outflux boundary that I was talking about before. And we call that time tau because it does depend really on the point and the direction. So if you change point and direction, you may get a different time, as you can just simply see from the picture. So we call this non-trapping. And here there is already kind of something quite nice that I mentioned as a sort of side remark. This already places an enormous restriction on the topology of your manifold. All of a sudden, it has to become something kind of simple from a topological point of view. And you can actually show, using some classical results of Champierre, that a manifold has to be contractible. So you might as well think that I'm actually working on some ball in Rn, basically. And that's good enough. But that ball has some geometry, and your geodesics might not be necessarily straight line curves, but they could be sort of deformed, filling the geometry of your manifold. So the other assumption that is quite common to do here that might play a role later is to what is called a simple manifold, and in which on top of the non-trapping, we don't want to have conjugate points. So basically it's that we don't want caustics to happen, so we want to rule out situations where the geodesic has a sort of focusing behavior like this within your manifold. This is something that we don't want, let's say. Another way you can think about this is that between 2 points, there's a unique geodesic connecting those 2 points. That would be totally equivalent to this assumption of having no conjugate points in this scenario. And here is what I was saying before, that again, if you don't like to think about this geometric setting, here is a bunch of examples that will be really good enough for what I'm going to say. Just think about a strictly convex domain in Rn, where you have just, let's say, the flat metric, and you can imagine the geodesics being line segments. It's clearly non-trapping. Every geodesic, every line exits in finite time. This is a bounded domain. We're working with a sort of compact scenario. But if you make a situ perturbation of this, you will preserve all these properties. You will have the convexity at the boundary, the geodesic will exit in finite time, and you will remain without caustics, without conjugate points. So that's one way to sort of, this is a sort of good class because it's a situ open class, it's large enough, and covers the situation in the Euclidean case, which is the origin of a lot of this. Okay, so that's the setting. And once you have the setting, you can introduce the X-ray transform. So this is just a generalization of the very classical Radon transform in the plane. But you can actually write it in this very general scenario in the following form. So you can begin this very generally by just taking a infinity function on the unit tangent bundle. So this is a function that depends on position and velocity. And you just essentially integrate that function along all the possible geodesics on your manifold. So here I am denoting by phi t the geodesic flow, which is just simply a way of packing all the geodesics together. So I'll just tell you very quickly what that is. So the geodesic flow of xv, all that you do, let me write it like this. Is that if you have a point and a direction, you take the unique geodesic with that point and direction, and you follow it after time t, and then you see where you finish. What is your point where you finish, and what is the final direction where you finish. So that gives you a sort of map from the unit tangent bundle to the unit tangent bundle. So then this is essentially, you look at your function along your geodesic, but now you're looking at position and velocity, and then you just integrate as you move all along the geodesic. So I was saying before, this is just the natural generalization of the Radon transform in the plane, which is exactly what you do. You have a function, let's say, in the plane with compact support, and you sort of integrate along all possible straight lines. What I'm actually doing here, just in this very simple line, is actually parameterizing all the geodesics from the influx boundary, because the set of directions, so again, if we had this picture, the set of positions and directions here parameterize all the possible geodesics, because since they all exit in finite time, you can sort of move forward and backwards and sort of go to either to a sort of influx point or an outflux point. So then you kind of think of this transform as taking a function on the unit tangent bundle and now producing a new function on the influx boundary, because it will depend on the position and direction that you shoot your geodesic from. Yeah. So that's exactly what happens in a CT scan. If you're putting a CT scan, the CT scan does exactly that to your body. So you throw X-rays in one particular direction, they get attenuated essentially by the tissue that they go through, and then the machine rotates, which means that you are scanning a two-dimensional section with all possible geodesics running in a flat domain in R2. So this is exactly the same sort of idea, and it gives you this natural transform. Okay, so I call this the X-ray transform. And in principle, this is very general. So one is actually sort of interested in particular cases where you take your function f here as being of a special nature. So the most popular are these ones. So the case really of the Radon transform in the plane is when you take functions that depend only on the position. So this is just a function on the configuration space, which is our manifold M. Yeah. So in this case, the function, rather than being a function of xv, it becomes just only a function of x. Yeah. But another very common thing is now you can sort of play this game and sort of allow different dependencies on v. Another very common one is you sort of allow a linear dependence on v. So this would be the case of a one form. Yeah. Or you may have symmetric two tensors where you have essentially, you can imagine that you have a tensor that I write in this form, let's say a symmetric two tensor, and then you can input in your tensor the two entries v, v, for example. So this is a situation that arises very often, for example, in geophysics, when you want to understand the geometry of the inner structure of the Earth, and you get into run into these sort of X-ray questions, and you want to understand really the X-ray transform acting on tensors of order 2. If you go to, let's say, sort of elasticity, you may run into tensors of order 4. So different scenarios will give you different things. So it's a good thing to have in mind that you can actually restrict this general X-ray transform to cover all these sort of possible scenarios. Definitely the most popular are the case of just functions that depend only on the position, one forms, which is, if you like, sort of the dual of vector fields, and then symmetric two tensors. Those are the three most important cases. And for those, I'm going to denote the X-ray by sort of I0, I1, and I2. So I will put this particular sub-indices. Please, if there are any questions or if nothing is clear about the background, please let me know. I'm very happy to answer questions as we move along. Okay, so this is the picture. So this is just to sort of summarize. You have your strictly convex domain. You have an influx point and vector going in that travels between your domain for a time tau. You have some function, maybe it's a function of x, or it's a one form, or it's a symmetric two tensor. You move that along the geodesics, and then you integrate, essentially. So that's the setting of the X-ray transform. Okay, now here comes, I guess, the first fundamental result that underpins everything, really, absolutely everything. And it goes back, sort of very interesting, goes back to the sort of 70s, to the Russian school. This is Mukhometov and then Anikonov and Romanov for the case of one forms. And they tell you the sort of basic sort of injectivity result that says that if you begin with a simple manifold, and it's very general, in any dimensions, so if you have a function whose X-ray transform is 0, when you go to sort of tensor of higher orders, let's say one forms or symmetric two tensors, it's very easy to see that these transforms have natural kernels, So there's a sort of obvious kernel for the case of one forms, essentially given by the fundamental theorem of calculus, that if you integrate a one form that is a potential, and the potential vanishes on the boundary, then you will get 0, because basically when you integrate, if you will get just the difference at the endpoints, but if your object has a sort of potential that is 0 at the endpoints, you just get 0. So once you leave functions and you go to higher order objects, one forms or tensors, you develop a kernel. So the best you can hope for in these sort of questions is to prove injectivity up to this natural abstraction, this kernel. And for one forms, this is exactly what this theorem says, that if the X-ray of a one form is 0, then the one form has to be potential, which essentially, or has to be exact, a sort of exact one form, which means exactly that f is of the form dp, where p is just a function that vanishes on the boundary. Now, I cannot emphasize how important it is, because this underpins everything, as I will try to explain. So this is the basic fundamental result. Now we know how to prove this quite well by using energy identities. If you want to know the proof of this, it is, of course, done in great detail in the book with Mikko and Gunther, if you want to take a look. And all the geometric background that I have just told you about is also described. Okay, so this is really this is the starting point. Great. Now, another very, very popular object that is associated with the X-ray is the adjoint. So this is the back projection operator, which is just the dual. So let me just explain that. This is a fundamental sort of operator because, for example, the inversion formula that Radon came up with 100 years ago does involve this adjoint I0 star. And in the literature of tomography, or it is called the back projection operator. Okay, now it's very easy to check that the X-ray that I defined to you in terms of infinity functions does sort of extend kind of immediately as a bounded operator between natural L2 spaces. Yeah. Now, to take the adjoint, you have to do something on the boundary, on the influx boundary, and this is to put a little weight here. So, so when you're at the boundary, you have a natural measure on the boundary, which is essentially, you take the sort of natural volume form on the boundary, and then essentially you take, a volume form on the sphere of unit vectors at the point. But then, to sort of consider the adjoint, you have to put a little extra weight, which is this mu. So you take that volume form and you multiply by that mu. So this is sort of kind of denoted by that mu there. And now you can compute the adjoint. That goes the other way. And I want to tell you that there's a very nice description of this adjoint for C-infinity objects. So if you were to begin on the L2 side, on the influx boundary with a C-infinity function there, with a suitable C-infinity function, you will land on C-infinity. And there is a very nice way to compute this adjoint in terms of transport operation. There's going to be a transport operator, and this is going to be the very first sort of simple PDE that will kind of arise in this situation. So let me run through that description for the back projection. And for that, I need to sort of introduce another two kind of key players that, again, give rise to lots of inverse problems. So on the influx side, we are going to consider not just all possible C-infinity functions on the influx boundary, but we're going to consider the restrictions of those defined on the entire boundary of SM that are actually invariant by what is called the scattering relation, which is essentially, again, one of the simplest things you can think about. Your geodesics go from influx to outflux, so they scatter as you go through the domain, and you measure that with a map called the scattering relation. This was introduced, I think, many decades ago by Guillemin. And you call this map alpha, and it has this very simple sort of picture. You take a point and an influx vector, and you just simply run through the geodesic through the sort of entire domain, and you look at the final point and the final tangent vector. So that gives you a nice diffeomorphism at the boundary, which is an involution, because if you were to run this backwards, since the geodesics are actually reversible, if you flip your vector, then you will run the geodesic in backward time. So if you were to sort of go backward, you will end up sort of something like that. And it gives you this sort of, nice diffeomorphism, which is an involution. The square is the identity, maps influx into outflux and outflux into influx. And that is the scattering relation. So those functions at the influx boundary, which are the restrictions of functions on the entire boundary of SM, which are invariant by the scattering relation, I denote them by this sort of symbol. These are functions on the influx boundary, and the subscript alpha is to sort of remind you that they are invariant by the scattering relation once you go to the entire boundary of the unit tangent boundary. So in that case, there's one other thing that I need to tell you before I tell you what the formula for the back projection is. Okay, so if you have a function on the influx boundary, it's very easy to produce a first integral. So this formula looks a lot more complicated than it actually really is. So let me just draw you a picture to make this less formal. So if you have information just at the influx boundary, you can easily construct a first integral for the geodesic flow. By a first integral, I mean a function that does not change along the orbits of the geodesic flow, which we'll write in a minute in terms of a transport equation. But all you do is, since you know that you're non-trapping and you exit in finite time, you just go backwards in time. Yeah, so this is all this sort of complicated thing. It's just simply going backwards in time, And you see you have a function here, W, which is a function of point and influx vector, and you just measure that W there. So it is clear, I hope, from the construction that, it doesn't matter where you begin and what point and what vector, as long as you are in the same limit.
Claro, ya está mal, ya. Ya está mal, muy mal.
Sorry, was that a question?
No, I think someone is
I had
just.
a microphone on. Yeah,
Yes.
that's
Okay.
yeah. So then you can define W on that sort of point and influx direction. And this has this sort of funny symbol, W sharp. So this is now a function on the entire unit tangent bundle. And now I can tell you what this back projection operator is. You essentially just average over you sort of do this first integral construction, and now you average over the sort of entire fiber. Yeah. And this is the dual of the X-ray transform. So let me just say this again. You take your function W here. Oops. You take your function W here. You construct this first integral by simply making it constant along the orbits of the geodesic flow, and now you just integrate over the fibers. So remember, the unit tangent bundle is points and vectors. So, there is, if you fix a point x in M, you have all the directions at that point. That is just simply just a sphere at the point, and you just integrate and you average. So now this gives you back now a function that depends only on position, because you have average over all velocities. And this is the back projection operator. Okay. So here is, now we sort of forward quite in time in the history of these developments. And here comes a kind of, fundamental result. And so this goes back to Pestovar-Nullmann, nearly 20 years ago, that they proved the following remarkable result. Now, this is a solvability result. It's not an injectivity thing. So it says that, well, now you have this sort of nice back projection operator going from these nice infinity functions. Now, it turns out that this is actually surjective, yeah? Which is, you are solving here, and as we will see in a minute, we are actually solving a particular PDE when we do this. So this was essential. I mean, I cannot emphasize. So I said before, the sort of injectivity result it is of course kind of underpins everything, but this other result by Pestovar-Nullmann changed the game, as I will try to explain in a minute. It has a very nice idea. I mean, I can even give you a sort of, like a sort of 1-2 minute proof of this, which is essentially, you consider now the normal operator associated with the X-ray, which is just simply you do I0 star I0. And it turns out that this is an elliptic pseudo-differential operator. You can compute the Schwarz kernel, and it turns out to be of order -1. So it makes things better, which is not too surprising because the X-ray you're actually integrating, so you're actually improving things. There are some boundary issues that you have to be careful here when you discuss the differential operators, but it's very easy to deal with this by sort of enlarging your manifold just a little bit. So you have your manifold with boundary, you sort of enlarge it a little bit, and you consider now this as a pseudo differential operator on your manifold without the boundary that is engulfing the manifold that you're interested in a little bit. And then once you know that this is an elliptic IDO and you know that it is injective, you are kind of in a linear algebra situation, almost like, you can say, well, I have an operator that is injective, then it's also going to be surjective. And, okay, so you are in infinite dimensions here, but once you have ellipticity and you put it into the pseudo differential calculus, then this essentially follows. Yeah. So that's the basic idea. This observation that is an elliptic IDO, well, here is where you use that you don't have caustics. Some of these things go back to Guillemin, but it's essentially Gunther-Ullmann and Plamen-Stefanov looked at this problem in great detail and proved lots of results in this direction. But this sort of the ellipticity of the normal operator is this sort of crucial thing. So this allows you to prove that this is actually surjective, and this was a sort of key result that Pestov and Ullmann used to prove the solution to the boundary rigidity problem in 2D. I'm not going to talk much about boundary rigidity because I don't really have the time, but I can tell you very quickly what it is. So boundary rigidity is one of those famous inverse problems in which, in the context that we're actually discussing, you assume in your problem that you know the boundary distance functions between 2 points, which is essentially saying that you know the tau, the time that the minimizing geodesic takes to go from the point X to the point Y. And from this sort of information, you want to reconstruct the geometry on the inside, which is exactly the problem in seismology that I was telling you about before. And this was solved by Pestov and Ullmann in dimension D, and the key result here was the surjectivity result of the X-ray, combined with other things that I will mention in a minute. Okay, so basically, I told you about the X-ray. I pointed out the key injectivity result from the 70s, and now we have this new thing that combines microlocal analysis essentially via SIDO and the sort of ellipticity to show that you have, in fact, a solvability for the dual of the X-ray. Okay, so this is also explained in the book if you want to take a look. Yeah. Okay, now the transport problem. What is the PDE that underpins all this? Well, it should not be surprising now that somehow, you know, the geodesic flow plays a role. The geodesic flow has a vector field associated with it, which is you just simply take the directional derivative of a C-infinity function along the flow. Like, you know, this is a very general thing. Just any vector field, you have a flow. The vector field induces a first-order differential operator between functions. In the setting that I'm talking about, that I have C-infinity Riemannian metrics, your X maps infinity functions to infinity functions, but the X, remember, lives in the unit tangent bundle. This is why working in the unit tangent bundle is so important, working in phase space. So that's your X. And a completely equivalent way to reinterpret the result by Pestov and Ullmann in terms of the dual of the X-ray is now in the following PDE form. So here it is. And going from one to the other is very easy. I'm not saying anything very deep here, right? So the deep thing was actually the surjectivity of the I0 star. But here is the way you can rephrase in terms of the transport. I call this, you know, a sort of transport equation, essentially, because you're moving along the orbits of your vector field. So the Pestov-Ullmann result can be reread in the following way. You give me as any C-infinity function on M, on the base space, on the configuration space, depending only on the position. And I can give you back, I can produce a C-infinity first integral living in the unit tangent bundle in phase space. And first integral is just the equation, the PDE X applied to W equal to 0. This is just saying that W is constant along all the orbits of the geodesic flow. Such that when you push forward this first integral, which is just sort of integration, that you get back the function that you gave. This is exactly the surjectivity. Yeah. So this pi is just simply the canonical foot point projection. You have a point and a position, you just map it on the base point. So there is a natural push forward of function, you just simply integrate. So this push forward here captures sort of integration along the fiber. And this is a completely equivalent way in which you can rephrase the Pestov-Ullmann result. So the Pestov-Ullmann result is saying that, okay, you have lots of first integrals, namely you can solve the sort of equation xw equal to 0, but you can solve it in such a way that once you push forward your solution, you hit all possible functions on the base. Okay, so this was up to now completely general. Now I'm going to move into dimension 2, yeah, for this sort of last part of the talk. Okay, so what happens in dimension 2? In dimension 2, you have something very nice. I mean, you have some of these features in higher dimensions, but in dimension 2 is particularly nice. You have this thing called the vertical vector field, because now in dimension 2, the picture that I had before, where you have your point X and then you have your unit vectors, obviously now in dimension 2, the set of unit vectors forms a circle. And since it forms a circle, and let's say you have an orientation on your surface, you have a kind of preferred way of traveling along that circle, and you can make perfect sense of, let's say, if you want to rotate by an angle theta, which means that essentially you have what is called a vertical vector field, which is simply just the vertical vector field that is tangent to the fibers now, which are now circles in your unit tangent bundle. Okay, now this circle action that you have in the unit tangent bundle allows you to do Fourier analysis in the usual way, in which all that you do is you just essentially freeze the point in the configuration space, you freeze X, and then you just do Fourier analysis just on the circle, on the fiber. But as you change your point X, you change your fibers, and then you have like a sort of parameter-dependent Fourier analysis. Okay, so in that way, you can decompose now L2. So L2 has a natural volume form, which is the usual, let's say, volume form from classical mechanics, if you like. There's no point in getting me into that. There's a sort of canonical volume form in the unit tangent bundle. So now you can decompose L2 into vertical Fourier modes, which essentially are each HK is the eigenspace that corresponds to minus IV. So the V actually, the flow of V actually preserves volume. So minus IV is a self-adjoint operator. And since I'm interested in this infinity objects, I denote those as omega K. And another way to think about this Fourier expansion is that you have a sort of Fourier mode U or something in omega K is a infinity function that has this sort of, the usual sort of behavior when you multiply by e to the it. So I think I told you before that I have multiplication by e to the it, or if you like, I can rotate by angle t. So if I have a function that depends on position and velocity, it is in omega k when it has this sort of behavior that you multiply by e to the it and you have an e to the ikt coming out, essentially. As it would happen if you were freezing X, that would be exactly what would happen with your Fourier mode. Okay, so this vertical Fourier analysis is very nice. So you can expand now any infinity function into this Fourier modes, vertical Fourier modes. So keep in mind now that this UK, they do depend now also on position and velocity, but they have this very special dependence on velocity. And now you can make the following definition. You can call a function U fiber-wise holomorphic, because you think about this as fibers. If the UK, if the negative Fourier modes are all 0 for k less than 0. And now there's this thing that the transport operator behaves exceptionally well with respect to this vertical decomposition. So there is this classical fact, going back to Gilliman and Cashen, that says that you can actually decompose the transport operator into two sort of operators that are essentially Cauchy-Riemann type operators, which I call eta plus and eta minus. And this eta plus and eta minus raise and lower the Fourier indices. So then the geodesic vector field has this very nice behavior. This is very general, works for any surface, but here it is just to sort of ground you in your intuition. What I'm saying is this very simple thing that you can just write down in the case of R2. In sort of applied math, anyone will write the transport operation as V grad X, right? This is the way you would say. Transport operator is V grad X. And you can write, this is a very trivial exercise to see that you can write V grad X in terms of this decomposition. You have D and D bar operator. These are the usual D and D bar in the plane. And then there is this kind of, this sort of thing coming with the Fourier modes that you have to sort of, to do the decomposition of V grad X, you have to sort of multiply the D, the D sort of operator by e to the I theta and the D bar by e to the minus I theta. And here you see exactly this thing that I was telling you about before. So this raises index by 1, this one, and this lowers index by 1 in terms of the vertical Fourier decomposition. Okay, but then since we are in the two-dimensional case, now your surface also has some complex behavior because it becomes a Riemann surface. Whenever you have a surface and you give it a Riemannian metric, and you have an orientation, you have the structure of a Riemann surface. You have multiplication by I on the tangent planes. This would be obvious in the case of R2. That's essentially this D and D bar, but this works in general. And now in this sort of language, a function in the base is a holomorphic function with respect to the structure of a Riemann surface, if and only if when you pull it back to the unit tangent bundle and you apply this operator eta minus, of Kilimin and Kashtan, you get 0. Which again, if you go back, you will be saying simply that, you know, a function is holomorphic when you sort of put it back and you sort of apply this D bar and you will get 0. Okay. Now, in dimension 2, the results of Pester-Ullmann has this following holomorphic upgrade, which is almost immediate, which is that if you begin with a holomorphic function on the base, you can actually construct now a first integral that is fiber-wise holomorphic, and when you do the push forward, you hit the holomorphic function on the base that you gave me. So this follows immediately from the Pester-Ullmann result because you just essentially cut off the Fourier modes. So in general, the W coming from Pester-Ullmann will have a Fourier expansion. You just essentially take the top part of the Fourier expansion, and since you know that the zero Fourier mode is holomorphic, you can check that it will remain a first integral because of all the properties that I just told you. So all of a sudden, you have this, the Pester-Ullmann result gets actually converted into something saying that you have a fiber-wise holomorphic function. You can construct now a if you have a holomorphic function on the base, you can construct now a fiber-wise holomorphic first integral with zero Fourier mode, the holomorphic function that you began with. And this is the way people have been looking at this for quite a while. And, you know, there's a bit of something not satisfying here because you have the notion now of holomorphic objects in sort of two directions. You have your holomorphic object on the base, but then you have this sort of fiber-wise holomorphicity. So this is essentially where the transport twistor space comes into the picture. So I think I'm going to ask how many minutes I have left because I don't want to sort of overstep.
I think not a lot of minutes because yes, how many minutes do you need?
I think I will try to wrap up fairly quickly. Okay.
Okay, 4 minutes it will be okay.
I think
Okay.
that should be fine for what I want to say. So basically, there is a way of kind of unifying all this, and this is what is called the transport twistor space. You know, you take the view that if you want to get to two truths in the real domain, you know, you have to create the right complex domain. This is the whole idea of twistor theory, where you try to complexify your picture. And basically, the message is that we've been able to do that. There is an underlying now complex surface that combines this holomorphicity in the horizontal direction and the vertical direction. The construction of this surface is sort of very natural. It's a sort of real four-dimensional manifold. It has a lot of very interesting features. It fits very well into what Treves calls involutive structures. From an analytical point of view, the really wonderful thing is that it degenerates at the boundary and picks up exactly the geodesic vector field at the boundary. And well, it turns out to be an object, you know, related to an object that in geometry has been studied by a lot of geometers somehow, going back to actually Hitchin and Lebron. And I guess what I just want to finish telling you is that what this really buys you is that now all these things that we were seeing before like, all this existence of holomorphic fiber-wise first integrals can now be completely translated in terms of the complex geometry of these complex surfaces. You can think now about just holomorphic functions on this complex surface, and this complex surface packs together the holomorphic structure of the Riemann surface, all this vertical Fourier analysis, and all this decomposition of the geodesic vector field using these operators by Guillemin and Kashtan. So there's now an object that underlies and underpins everything. And all the previous results now on geometric inverse problems can now essentially be rephrased in terms of this complex surface. And basically, a lot of the research that I've been doing in the last 3 or 4 years have been essentially trying to sort of exploit these complex surfaces, because it gives me a way to think about a lot of these problems that we didn't have before. So this is sort of opening up a lot of avenues for research. So I think I will definitely stop here. Sorry that I went over time a little bit.
Okay, thank you very much for this wonderful talk. So let's ask the audience if they have any questions. Please, you can use your microphone or also write your question in the chat. Okay. Johnny, have you a question?
No,
We
I
have-
was clapping only. Thank you.
So I have a probably short question. I don't know if we can use somehow numerics in order to reconstruct the unknown manifold, or if there are some techniques that we can use for it.
Yeah, I mean, there's the answer to that question is could be very long. I'll try to make it short. There's tons of techniques. Depends on the particular sort of inverse problem that you've been looking at. What I can say is that one thing that I got involved that with a lot of these geometric inverse problems is to use a Bayesian inversion, where you use essentially statistical methods to reconstruct this. And yeah, so if you're not in a rush, the Bayesian method works very well, because you can run your, if you don't have any rush running your Markov chain, you can certainly do that. And this particularly suited with a lot of these geometrical questions, because you don't have inversion formulas. So in the random case, you have an inversion formula. If you have an inversion formula, you will use the inversion formula. And that works extremely well. That's what the CT scans do. But the moment you go into these sort of geometries or problems in geophysics that you don't know what the internal geometry is, the Bayesian method could be an effective one. So I have implemented that with for some of these X-ray questions, and it's actually quite good. But that doesn't mean that this is what you have to do. This, depending on I think really the answer to your question is depends very much on the problem that you're looking at. But yes, the numerical side of inverse problems is massively developed. The great thing about the Bayesian inversion is that it applies to anything.
Yeah.
And we have now very general guarantees that will allow you to sort of say that what you're using is actually legal.
Okay, thank you very
Actually,
much.
I have one question. I saw in this last frame that you were mentioning the complex analysis use of in this research, and I saw that here you mentioned the holomorphic functions. And how important is the holomorphicity in this research or the part of complex analysis?
Oh, it's actually fundamental. I mean, I think that I can even tell you the answer that, if you're thinking about a geometric inverse problem in 2 dimension and you don't think in these complex geometric terms, you're missing out. I mean, it's exactly the same thing as, trying to compute an integral and not using residues. I mean, you want to use, this is really the way to do it. So this is a little bit like the same thing. I mean, so once you have this holomorphic object in the background, it will definitely guide you and it will make everything look simpler.
Yes.
So, like for example, that proof of Pesto and Ullmann of boundary rigidity, there's a completely twisted proof that you can give, like, you can draw a diagram and you can see now what they proved. Basically,
Yeah.
they did it in from a real point of view because they were not thinking in these terms.
Because holomorphicity is a very local, locally is very important and very powerful property, no?
Indeed, but keep in mind that here is holomorphicity in several complex variables. I mean, several, I mean two.
Yes.
But there is a real difference between, we are looking now at, because what we have really is a complex surface.
Mm.
So these functions here become sort of holomorphic functions in two variables. So this is why, they get killed by two objects, basically.
Mm.
One object which is horizontal and one object that is vertical.
Mhm. Thank you.
Sure.
Thank you.
Okay, so thank you very much again. So if there are no more questions, we thank you again for your wonderful talk, and
Thank you.
thank you for being with us.
Thank you. Okay, so I guess I'll stop sharing and
Yeah. Diego have